Cool, then let's start with the lecture. So I'm substituting Professor Fry today to give you a short but hopefully kind of intuitive introduction into more advanced sampling techniques and how they are related to stochastic processes. So obviously this is not a machine learning lecture, but many areas of machine learning use different kinds of sampling methods, and I will show you today what they are for, so why we need to use them. And at the end of the lecture, hopefully you will understand how we can use our physical intuition and our knowledge from stochastic processes from this lecture to understand this kind of machine learning tools or this technique, really. It's not a kind of one-use technique. You can use it for many different things, and we're going to talk about that. But first, let me show you one or pose you a problem that we're going to try to solve, and then you will see why sampling methods are necessary to solve this kind of problem. So here you see two animals which used to live also in Europe. Nowadays they're kind of rare, but they also live in North America and other parts of the world. The lynx, a kind of wildcat, and the hare, which is kind of like a rabbit. And the lynx usually feeds off the rabbit, so they hunt them and they eat them as their prey. And now imagine you run a company, and in fact, until like over 100 years ago, or starting over 100 years ago, there is a real company. This is not just made up. The Hudson Bay Company is called, which used to hunt both of these animals and get their pelts and then sell them. So on the right side of the slide now you can see some historical data that the company recorded with how many pelts, so that the fur of these animals, they hunted and they sold in a given year between 1900 and 1920. And now you might ask yourself, if you run this company, how can you predict, how many sales you can make in the future based on the historical data, right? That's a very relevant question for you as a business person. So how can you understand this? The first way of understanding data is usually plotting it, not just looking at it in the table. Then you realize there's some periodicity here. And the population of the hare goes up a little bit, but then shortly afterwards, with a little offset, somehow the lynx hatches up. But then at some point, the hare population goes down again, and also the lynx population goes down. And it somehow seems like it repeats in a cyclic manner. And some people came up with this toy model, really, of this process, where you have a predator species and a prey species, which we call Y and X here. And I think you have seen this, or at least a version of this equation also in the lecture already. These are called Lotka-Volterra equations, or models in general. And we're assuming now that this model somehow captures the dynamics of these two species. Of course, this is a very big assumption. There are many things that we neglect here, like the environment. We're only including the reproduction of the hares. So this is the term alpha X. So the hare has some production rate. Then the feeding process, the lynx feeding on the hares, is the X times Y term. So the hares get consumed at some rate, and the lynx can reproduce by feeding off the hares. And if there's too many lynx, they somehow compete with each other. So the more lynx there are, also the faster they're going to die out, because somehow they have to compete for resources. And that's why there's this decay term here. If nothing happens, the lynx will just die out if there are no hare over time. Now, actually, if you look at the whole time series, not just 20 years, but there is data for over 100 years actually, you will notice that it's not always perfectly periodic, and there are some very large fluctuations sometimes. This is not what we're going to discuss now. That's why I conveniently picked these 20 years, because you can actually find parameters, alpha, beta, gamma, delta, that somehow fit this data very nicely. And my question to you is now, how would you find these parameters? What would you do if I am your boss in the company and I tell you, hey, how many links will there be, in 10 years after 1920. So how should we allocate our funds in the business? What's your approach? You had this model, you had the historical data. How can you find out what's the most likely course of data in the future? Just very generally. This is not really what we did in the lecture, just gut feeling. What's your approach? Yeah?
You have to figure out the model parameters.
Yes, so
I guess alpha and beta, and you can choose probably the most likely ones if you're lucky.
right? So, and I'm just going to repeat it for the recording. We had to find the model parameters. That's essentially our job. How many are there? How many model parameters? Four? Yes, slightly trick question. Obviously, there are these four rates, but actually there are more parameters that we don't know, which is, on the one hand, you can see the data is not perfectly periodic, right? So the first peak is a bit higher than the second peak and so on. So there will be surely some noise in the distribution. What we're recording here, or in the data, sorry, so in the measurements there's some noise. What we're recording here is the number of pelts that we sell, which is not automatically the number of animals that roam around in the country, right? One year we might be lucky and catch a few more, next year we might be unlucky. So there are measurement noises that we don't know for both of these measurements. These are two extra parameters that we have to infer if we want to really say, oh, you know, this is the most likely scenario that we recorded. There are two more, which are the initial conditions. You could say, oh, I just look at the 2 points here, where my time series starts, but we already said they are noisy, so we don't really know the exact initial conditions, which means these are also two free parameters that we need to figure out. In order to simulate these equations, we need to put exact initial conditions that we don't know. So even in a small model like this, there's only 4, let's say, reaction parameters. There are actually up to 6 or 8, depending on what you want to include, or even more parameters that you need to infer if you are really trying to solve this problem, you know, in a holistic way, let's say. Right, so this is the problem I'm posing to you, and I want to walk you through how we try to solve it, and at which point we need to sample something from probability distributions, and why this is very conveniently done with stochastic processes that we already saw in the lecture. Okay? And for this, I'm going to continue on the blackboard now. And if you have questions, please interrupt me at any time, right? But I hope so far everything is still clear. Right, so we have this motivating example, let's say. Of, let's say, we want to infer model parameters from some data. Could be this example I just showed you, could be any data, really. You could even go one step further and say, well, if we don't really know the model yet, you could also say, well, what is the right set of equations that fits this, right? And then you could try to somehow parameterize your yes for an equation and then try to find the right terms in the equation. Basically, the world is your oyster. The more complicated you make it, the more parameters you have to infer in the end, right? So, put a different way, sorry. Given the data, and we also heard this from your colleague right now, what are the most likely parameters? And most likely is something I have to somehow specify, right? What do I mean most likely? Do you have any idea what I'm trying to get at here? What kind of thinking or kind of techniques are we using if we're talking about likelihood and probabilities of certain model parameters. This is a certain way of thinking that is really used all throughout modern machine learning techniques that I'm sure you're also familiar with from your studies or even from high school mathematics. What kind of techniques are we using? Sorry?
Mean square root of
the mean square root? Yes, this is going to show up at some point, but more in a broader sense. So what type of picture are we using? And I'm basically saying, well, the data is somehow, there's some noise in the data, but I'm also saying that parameters themselves are some random quantities that have some likelihood and some probabilities. What am I doing here? Sorry? Yes, so this whole way of thinking about the problem usually is called Bayesian statistics or Bayesian probabilistic thinking. So what I'm going to do at the start is I'm going to basically formulate the problem in the Bayesian way, which is a fancy way of saying I'm going to use Bayes' theorem, which you all know, I think. But if not, that's also no problem. We're just going to write it down. And then I'm going to explain the terms in a moment. So this is a mathematical identity for probability distributions. It's very general. It applies to basically everything. The intellectual step comes in when we say, this here are the model parameters, the thetas, or actually, sorry, let me write it down here. So theta are the model parameters. So, this would be the reaction rates, could be initial conditions, and so on and so forth. And claiming that there is a probability distribution of these parameters, right? This is not something obvious, and maybe it's not true in a philosophical sense, but certainly we can use this as a mathematical tool to formulate our problem in a way that we can later use the techniques that we already know about stochastic processes. Right, so these are the model parameters, and E is what I call the data. So in the example that we just looked at, these are the time series, the table that you saw, right? In this year, we had so many pelts, and the next year, we had so many. And then these elements here, I'll write it down here, that's easier to see. It has certain names. The names themselves are not so important, but rather the meaning of them. So this is often called the likelihood. Of these model parameters. And this basically encodes the model for us. The model and the experimental setup, the measurement process. I'm not going to go into detail here, so if you take a course on Bayesian statistics, you're going to talk more about this and what kind of form this usually has. And this is where the least squares method comes in at the end. So very often, this likelihood is some kind of sum over the prediction minus the real data to the squared divided by some measurement error. This kind of thing. It doesn't really matter what it is for us now. It's some function that depends on these model parameters, but it's not a probability of the model parameters because they are the condition here, right? The data is fixed. The data is what we have. But the parameters are here on the right side, so that's why we don't call it probability, but rather likelihood. It's not normalized over the parameters, right? then this PR of theta is often called the prior. We have to input in this relation here with what I didn't mention should give us in the end the probability that these are the model parameters that we're looking for, given this certain data. We have to input some prior information. So what do we believe about the parameters? What's their possible range, let's say, before we actually collect the data. So there's no conditional here at the moment. Just the prior information. So this holds all the prior knowledge about the parameters. And this P of E, the name is sometimes evidence. Again, the name itself doesn't really matter. It's a very weird thing, right? If you think about it in the big picture, it's the probability that we recorded this data. How can you interpret this, without any additional context? So that's why this is one of the reasons why often we neglect this evidence and don't talk about it a lot. And it turns out you don't have to in many cases, because let's say you want to know the most likely parameters, right? What do you want to do? You maximize this expression with respect to the parameters. So you maximize the right-hand side, but this is just a normalization constant in terms of theta. It doesn't depend on theta. So the maximum in theta will always be at the same position no matter what the value of this evidence is, right? So in many cases, we don't actually care about this when you only want to know the most likely parameters, or so to say, the most likely curve that goes through your data points. What's the problem though? For you, the problem might be if your boss says, I don't only want to know the most likely parameters, I want to know, let's say, what's the range of parameters that is, 80% likely, so that I want to have some confidence in my prediction, right? I don't only want a single number and say, this is alpha, because I know it's not going to be exactly the right value anyway, because there's noise and there's, some things I neglected about the environment. I want to know some range, right? So this here, the normalization, can often be neglected, but in this lecture, basically, this is what we're going to hear about, and then I'll show you what I mean by that. So it can be neglected if you're only interested in, let's say, the maximum, but not if you're really interested in, let's say, the average of the distribution. So now we're wondering, do we actually need this? And if we need it, how can we deal with it? Then continue here. Right. So what if let's say the average or the variance of theta, or any other average of some function of theta that we're interested in, right? Anything like this. If we're in this situation, we cannot just ignore the normalization. It doesn't matter if the average is this number or 10 times this number, or 0.1 times this number. So we're interested in calculating expressions of this sort. Now I'm dropping the condition on the data. Okay, so this is still the full posterior distribution that I wrote up here, but I don't always want to write the condition on data because it's going to appear a lot now. That's why also I hold this PR of theta and not just P of theta. Usually everything is called P in statistical courses, and it's very confusing. But this is really the same object that we had before. This is actually P of theta given the data, okay? And then times the function that we're interested in. Could be the value of the parameters themselves, could be anything else, right? If you want to know this, you need to correctly normalize distribution here. Otherwise, you just get a wrong answer by this normalization factor if you don't include it. Okay? Why is this so difficult to calculate? Any ideas? So this is, in general, a very difficult expression to evaluate. Because, yes.
You might have very many parameters, so it's a very high dimensional integral.
Exactly. So let me write down, because usually at least one of these things is true. These reasons. And one is certainly high dimensional integral. So n, I call this n here, the number of parameters. We saw even in this very simple example, you only have two curves that you want to fit, and a model that looks very small, but it had, let's say, 8 parameters. So this is, in the end, the 8-dimensional integral, which can be tricky to solve. Any other ideas or intuition why it's tough? It's somehow related to this, but if you think, why is it so hard to integrate something in 8-dimensional space compared to 1 or 2 dimensions?
Well, for numerics it's hard.
For numerics it's hard, and yes, but I'm gonna just give you some kind of intuition why it's hard, hopefully. So very often you don't only have high dimensional space that you're integrating. You always also have large domains usually of your parameters, right? And this problem, so let's say your parameters are all positive numbers, right? They are reaction rates. They hook to 0 to infinity in principle, right? You're gonna restrict it with the prior, but this problem gets amplified exponentially by the high dimensions. So if you have one parameter with a large space, that might still be fine. If you have 8 of them, you have to the 8th power, basically, this domain. And another one in practice, and maybe this is also what you mean by numerically it's hard. The computation of the function inside the integral might be expensive or might take a long time. For example, if it's a simulation, if we go back to the example from the start, it's an ordinary differential equation that predicts our time series. So to test or to evaluate this function for one set of parameters, you need to solve this differential equation at least once. And depending on what your problem is, the simulation can take quite long, right? So if your function is very expensive and you have to evaluate it in this integral over a large domain in high dimensions, you're always going to run into trouble with this, let's call it naive integration. Of course, there are smarter ways of doing this, but this type of integration is usually problematic for these reasons. So if you're going to say this integral over n-dimensional space is roughly a sum over little delta theta to the power n, So we're discretizing space, and then it's just evaluating the function over the whole space. This quickly doesn't work if this is, very large, or the deltas have to become very small compared to your domain. And let me just draw the picture. So naive integration doesn't work. That's the problem. And why? Just to give you a better maybe visual understanding, let's say in 1D, this is your parameter space, and let's say the function where the function is not zero is mostly in a certain region here, just as an example. This is basically where the meat of the integral comes from. And outside, the probabilities are mostly zero, or the likelihood is mostly zero. This looks fine, but in 2 dimensions already, let's assume in each direction that the parameters will have a similar extent. Already the volume fraction of this little blob in the 2-dimensional square is a lot smaller. And the more dimensions you add, the worse it gets. So if you imagine a hue, and this is all just very, hand wavy, but I think you all have an intuition about this going to higher dimensions, that volume has some weird behavior sometimes. Right? So if you keep adding more and more dimensions, because the probability is normalized, somehow the volume where most of the probability lives, if you want to call it that, is going to shrink relative to the whole parameter space. Right? This is just something very generic that happens in high-dimensional spaces. And the area where there's basically no relevant probability whatsoever is going to increase relative to the interesting part here. Okay? So now taking a grid and doing this integration here, basically discretizing the space, is wasting a lot of computation, because evaluating the integral in any of these little squares will give you zero. So it's a waste of time basically to calculate this expensive simulation or let it run in all of these areas. Ideally, you would like to only evaluate it where you already know that you have a high contribution to the integral. Okay, does this make sense? So this is why we cannot just do numerical integration as we normally know it. Okay? So let me just also write it down. Evaluating f of theta times u of theta here is a waste of resources. Right? You're spending most of your time calculating zero probabilities and adding them up. That just doesn't really make sense. What's a smarter way to do this? We already kind of talked about it. You would like to just look at the points where the probability is actually high, if possible. And maybe you know one example of this. So if you have seen this demonstration, when you want to know the value of pi, for example, the number pi, you can draw a circle and a square around it, and you uniformly randomly throw points at the square, And in the end, it's just how many are in the square and how many are out of the square. And the ratio of that gives you the ratio of the area of the circle and the area of the outside. And since you know that the area of the circle should be related to pi, you can stochastically approximate pi in this way. Okay? And this is exactly what we're going to do, just in a slightly more sophisticated way. Because doing it this way that I just described also doesn't work for another reason. Okay, so anyhow, what we're going to do is Monte Carlo integration. That's sort of the umbrella term for different techniques that are all along similar lines. So we're taking this integral over some function and also the probability. Yes. So this is the average or the expectation value of f, right? And we're going to say approximately, if we have enough samples, this is really just evaluating this function at different points. Sorry, let me write it like this. And then divided by the number of samples. Okay. And this I here is a set of samples from the distribution. So if you have some way of generating randomly points from the distribution that you're interested in, then you can just do an empirical average, right? You just sum up, it's like throwing the dice. You roll the dice many times, you sum up the values and divide by how many times you rolled it. That gives you an empirical approximation to the real average. And the law of large numbers says if you do this enough times, eventually it will converge to the true value. Okay? But how do we generate these samples? That's the real question. So how do we generate these theta I values? In the case of certain distributions, it's very easy, right? Uniform distributions, we just call a random number generator. Gaussian distributions you can also generate exactly by just calling some function on your computer. But what if I ask for this distribution up there, the one that we talked about in the beginning, that I only know as a product of some likelihood and some prior divided by some unknown number that I cannot even calculate. To solve this problem, we have to give up one thing that I forgot to mention. Ideally, these samples are all independent, right? So you should do independent draws from the distribution, then you certainly know that this will converge to the right value. If we give up this requirement that they have to be independent, we can do a little trick, and that's the whole point of the lecture. We're going to construct a Markov chain, or Markov process, depending on how you want to call it, that has as its stationary distribution the one that we're interested in. Okay? And we're going to see why this somehow makes sense and solves our problem. Stationary distribution. And I believe last week in the lecture you talked about one example of this in kind of in the context of the Bayesian model. Is that true? Yes. I think last week on Thursday you talked about a version of this in the Bayesian model or some other equilibrium systems, right? Okay. So the basic idea is exactly the same, and just on a recap, what we're doing here. So now we've gone from this general problem of, inferring some parameters to figuring out we need to calculate some integrals that we cannot calculate. So we need the Monte-Carlo integration. And now we're at the point where standard Monte-Carlo integration doesn't work because we don't even know how to sample from the distribution. So that's how we arrive now at the name of these techniques, which is called Markov chain Monte Carlo methods. And the whole rest of the lecture, like 1 hour, is going to be about these methods. Or in particular, one, kind of like how does it work generally, and then two, the Hamiltonian Monte Carlo method, which is kind of one of the more modern ways of simulating this. They're very often abbreviated with MC because it's such an unwieldy name. And some people also call it Monte Carlo Markov chain if they talk about one Markov chain. So yeah, anyhow, you can switch around MC and it's still the same. And the basic idea that we already talked about in words is we need to somehow construct transition probabilities. So now this is not the parameters given the data. Now I use the same letter P that I mean something else. This is a transition probability in the space of the parameters, okay? In this little high-dimensional space that I sketched over there. So transition rates such that we need to ensure two things that you also, I think, talked about in the last lecture. And now basically we can use our intuition from stochastic processes, because suddenly we're talking about a Markov chain, which we already studied in the lecture quite a while. So we need to explore all of the parameter space, right? If we cannot reach certain regions in our space with these transition rates, then certainly we cannot get the true, correct samples from the distribution.
Is that the irreducibility chain?
Yes. So this is exactly related to this condition of irreducibility in Markov processes that we also talked about already. And it's going to cycle back to this construction in 1 minute. Just the second requirement is kind of almost trivial, but I'm just going to write it down. So we will find any state, now how the state or parameter set theta in this chain with the probability P theta. So what I mean is it really does have this distribution as a steady state. So if you let it run, you have a whole collection of samples, and the probability to find any even sample in this chain is exactly the true probability. Okay? And these two conditions hold, in a certain sense, exactly what your colleague just said. You need irreducibility of a Markov process, which is related to this condition on a high level, to ensure that it does converge to a unique stationary state. Okay? And we're going to use this. So this is why this works in another, if you want to put it differently. Because such a process has a unique steady state, and we're going to construct it such that the steady state is our distribution that we want. Okay? Now let me just give you the answer, and then we can take a short break, I think. But I just want to finish this. part, so you know what you can imagine, and you can also appreciate that this is more general than what you saw in the last lecture. We can not only sample from equilibrium distributions, we can really sample from arbitrary distributions like this. Okay? Of course, I'm not a mathematician, so when I say arbitrary, there are some conditions that we have to check, like it shouldn't be too weird, I guess. But yeah, you know what I mean. So what is the algorithm that we're going to use to generate these samples? First, you pick any point in your state space, so theta 0. My handwriting is really bad, I apologize. And then for as long as you like, basically, I'm going to use some kind of pseudo notation. So for some duration, for some number of iterations, you do the following two things. You propose a new theta, let's call it theta prime, with a certain probability that we're going to call Q. So if you are at theta, at this initial theta 0, and actually later we're going to be at I minus 1. So at the previous iteration, there is a certain distribution of new proposals that we're going to make. Okay? And then with a certain probability, again, another probability, let's call this A. And this expression, either 1 or a number smaller than 1, and I'm going to show you in a moment what this number is. Accept this new proposal. So then theta I is just theta prime. Otherwise, you reject it. So your theta I is going to be the previous one. And that's it. So you keep doing this, and then the output of this is some list of thetas. Theta 0, theta 1, and so on, until theta n. And this is what we then call our chain, basically. And if you let this run long enough, and usually you have to throw away the start of this chain, otherwise, you have a random arbitrary starting point, which is probably not very likely to be in your distribution. So let's assume we throw away the n, then picking any theta out of this list will happen with a certain probability given by p theta. We haven't really shown, or we haven't really shown if this is true or not without talking about this acceptance probability, which we're going to do in about 10 minutes. Let's take a short break here, and then we're going to come back to that. But so far, everything fine? Okay. Then after the break, or actually, maybe let's say 5 minutes because we started a little bit late. So I just clean the board and refresh yourself. And then you think about what this alpha value would be, and then we're going to continue.